And let me do a quick review on the whiteboard of what we were talking about last time. So we are talking about torque. And we define torque with the symbol tau as R times F times sine of theta. And just to give you an idea, a picture to go along with that, if I have an object, doesn't matter what the object looks like, but it's pivoted at some point, and then I apply a force at any other point, any place other than the pivot, and we can draw a vector R that goes from the pivot to the place where our force is connected. And there's an angle theta between the direction of R and F. And it doesn't really matter which of these angles we choose because of a peculiarity of the sine of theta, the sine function. If it were the cosine of theta, we would have to pick this angle here that is between, if we would move R so that it starts in the same place as F, it would be between R and F. But for us, it turns out either of these is okay, and so whatever's more convenient. That defines the torque. And we are working on static problems primarily, exclusively in this chapter. And for a static problem, we know that net force equals 0, and now also net torque equals 0. So that's the basic idea here. We're going to practice today with a whole bunch of different problems with different geometries, but the equations of this chapter are always the same. Net force equals 0, net torque equals 0, and we are typically solving these to find the magnitude and direction possibly of some unknown forces. So let's start today by talking about a problem with a ladder. So suppose we have a ladder and it leans on the wall of a building. Maybe the angle it's making with the ground is 70 degrees. So that means there's a 20-degree angle with the wall. And suppose the mass of the ladder is 20 kilograms and the length is 10 meters. So we have a length of 10 meters. And what I'd like to find is the coefficient of friction that's necessary, the minimum coefficient of friction that's necessary for this ladder not to slide. Okay, because if there's not enough friction on the base, the ladder's going to slide out. So if I want to pursue this problem, it means we have to draw in all of our forces. So there's the force of gravity to begin with. And the force of gravity will go right in the middle of the ladder. And generally, we'll assume that unless the problem's otherwise. We'll assume that the force of gravity is located right in the center of the object. Then we will have on the ground, there's going to be some kind of normal force where it's, making contact with the ground. And there should also be some friction down here. And to know which way the friction goes, we have to think which way is the ladder, the base of the ladder, going to go if there's no friction. If there's no friction, it's going to slide to the left, and that means the friction must be pointing to the right. And then finally, up here at the location of the wall, there's some kind of contact force. Normally, when we see a problem like this, to make it easier, we say that the wall is a smooth wall, which means no friction. So if there's no friction, then there's going to be a normal force on the wall. And I would just call that N wall. Maybe call this one N, I don't know, we'll call the other one N, and this one will be called N wall, just to keep in mind, they might be different. And those are the only forces, right? Because there's only contact at the two ends, and then there's force of gravity. And so we have friction and normal on the bottom, that sort of represents one force of contact. The other force of contact is only a normal force because the problem, to make it easy for us, says it's a smooth or frictionless wall. So that force has to be making a right angle to the wall. And that's it. Now we want to find the coefficient of friction. So we have a couple options. We can use net force equals 0, or net torque equals 0, or possibly both. What we saw last time is that sometimes just using torque is enough. So let's try to just use torque. Say net torque equals 0. And in principle, there's 4 forces, so there would be 4 torques. There would be a torque from the wall, a torque from gravity, a torque from the normal force, and a torque from friction. Okay, so those are the 4 potential torques. But I have to choose a pivot point before I can torque. And when I choose the pivot point, I'm going to be able to eliminate at least one of these torques. Okay. Does anyone remember why choosing a pivot point in a particular place allows us to get rid of one of the torques? Remember that? Raise your hand if you remember it, but you're just not feeling energetic enough to say it. Nobody remembers that. So it's happening when we are in a situation where the R value is equal to 0. So if R equals 0, then there's no torque. So that means if, for example, I pick the center of this ladder as my pivot point, then the torque from gravity would be able to be canceled out. If, on the other hand, I pick the corner up here where the wall is, I could cancel out that normal force. And if I pick the point down here, I can cancel out actually 2 of my 4 torques. So I can at least always get rid of one of them. Now, it's not always clear which one I should get rid of, but it's also true that there's not really a wrong way to do it. It's just maybe a good way and a better way. So I would say, for me, if I'm looking at this problem, I would have kind of 2 ideas. I might pick the bottom left corner as my pivot point, with the reasoning that if I do that, I'm going to be able to cross out 2 of my torques. But maybe I don't want to do that because the thing I'm looking for is coefficient of friction, and if I cross out the torque from friction, the thing I'm looking for just drops out of the equation. So maybe I don't want to do that. Maybe then the other one would be maybe to pick the top right corner because I don't really know what the normal force from the wall is. That would also be okay. Both of those options would be just fine. And neither one of them is going to probably get us where we want in one step. So let's take the second one. Let's put the pivot point at the top right and see how that works. But you could also definitely pick the bottom left or even the center. So if I do that, the torque from the wall cancels out. And now that I've chosen the pivot point, I am allowed to determine the signs of these torques. So we remember that torque is going to be positive if the force would make the object want to go counterclockwise around the pivot point. Even though this thing's not moving, we imagine it could swing around this pivot point. So if a force would make it go counterclockwise, which is, this way, then I'm going to give it a plus sign. And if it wants to go the other way, it's going to get a minus sign. So go ahead and fill those signs in on your own on the paper first, just to test your thinking on your notes. And then I'll fill them in. Okay, so let's start with force of gravity. So if I look at the force of gravity and imagine the top edge is the pivot, force of gravity is trying to bring the ladder down, trying to make it more vertical, which means it's going around like this, and that's going to be counterclockwise. So torque of gravity is going to get a plus sign. Normal force is trying to do the opposite. It's trying to bring it around the other way, which ultimately is clockwise. So that's going to get a minus sign. And how about friction? Friction also tries to make this ladder more vertical, which would be rotating in the counterclockwise direction. So we get a plus sign. Raise your hand if you got the same signs that I got. Okay. So what now? Well, now I'm looking for mu, and I know that's going to be inside of the friction. So I'm going to get the torque friction by itself by just moving things around. Torque friction is equal to torque normal minus torque G. And then once I've done that, I write down the formula for torque in each case. So that's going to be R friction times sine of theta friction. So I basically just write RF sine of theta once each for each torque, and then put little subscripts there. So we're going to have R normal times the normal times sine of theta normal minus RG FG sine of theta G. So the labels that go on the R and the theta just are there to agree with whatever the force is. And we just label them whatever way is going to make it sufficiently clear to us what we're talking about. There's not really a wrong or right way. Just you could call these forces force 1, 2, and 3 and give labels of 1, 2, and 3 if you really wanted to. Then we want to solve for mu. So mu is showing up in the friction. So that's going to be RF mu times normal. Which normal would it be? It would be the one that's connected to the friction. So the one that's just called N. Mu, RF mu normal sine of theta F equals, on the other side, Rn N sine of theta N minus Rg. Let's call this M times G, just to save ourselves a little bit of work later down the road. And that's our equation. We have to solve it for mu. So if I just copy this onto a new page, okay, so there it is. We could just rearrange it and solve for mu. Mu is going to be equal to the whole right-hand side, Rn N sine of theta N minus Rg Mg sine of theta G all over Rf, not mu, N sine of theta F. So there's my expression, and all I need to do now is to know if I got, if I know all of these numbers, and so that I can plug them in. So what I like to do, make a table. So we need to know Rn, we need to know N, we need to know theta N, Rg, M, theta G, and then RF. Well, there's N appearing twice, so I don't really need to write N again. So I just basically went through this and listed every symbol that I have. And now we want to go through our picture. We reproduce our picture on the same page. Okay, that should be good enough for me to measure stuff. So Rn, what is that exactly? Well, that would be the length of a vector that points from my pivot point to wherever the normal force is. So that would be Rn, that green vector that I just drew. That's just going to be the length of the ladder, which we know. How about the normal force? Well, we don't necessarily know the normal force, so we would have to solve for the normal force. How do I do that? I just do sum of the forces in the y direction equals 0. That's normal minus Fg. So normal is equal to Fg, which is equal to m times g. So that's going to be mg. The theta for the normal force. So I look at my picture, I've got my green vector and the normal force, and the angle between them. Since we have a 70-degree angle down here, there must be 20 degrees on top, 20 degrees for theta n. Then how about Rg? That's just going to be the length over 2 because the force of gravity is right in the middle. I'm just going to call it m because I'm noticing that the m's and g's are going to all cancel. So, but we could put it in here if necessary. How about the theta g? Well, we need an Rg. We maybe do that in blue. So Rg, that's the L over 2. And the angle between that one and the force of gravity, I'm looking at this little angle here. That's going to be 20 degrees. Or you could call it 160 degrees if you want to get the big exterior angle. Then for our friction, that's from the pivot point to where friction is located. Notice that's exactly the same as our normal. So I'm not going to draw a new vector for that. But we can see that that is just going to be L from the pivot point down to where the friction is. And the theta for friction, that's 70 degrees. So if I put all of this stuff in, we have L. For normal force, we have mg, sine of theta n, which is 20 degrees, minus Rg, which is L over 2, times m times g times sine of theta g, which is also 20 degrees. And we divide this by L times the normal force, which is mg, times sine of, in this case, it's 70 degrees. Sine of theta f is 70 degrees. So because I worked all this out in the table, it's very easy for me to put things in and see what's happening. And I can see that the mg's just cancel. And I can see that L just cancels. And so on the top, what I get is sine of 20 minus 1/2 times sine of 20. And on the bottom, we have just sine of 70. So on the top, I can simplify that to, sine of 20 minus 1/2 of sine of 20 is just a positive 1/2 of sine of 20. So when you have like something and you subtract off half of that something, you still have half of it left. And then we divide that by sine of 70. So let's see what we get. We get 0.182. Okay. Any questions? Haley.
So whenever we're in the R, we don't have to do like tip to tail like we usually do for vectors. We're drawing it like to the origin of where that vector is starting.
R, you always draw R. We're not adding vectors. Okay, we're not adding them. We're just drawing them so we can see the angles between them. So when you draw R, you always put the tail of R at the pivot point. And then the head is going to go wherever the tail of, its associated vector is. So it still looks like you're adding them, tail to head. But we're not actually adding them. We're just kind of placing them. Okay, good. Other questions? Ziad?
So for friction, for our friction, you mentioned that even though it's going in the same direction as N force, that it's L, like it's length L. How come it's over 2 as the N force? Oh, N force is L. My bad. I didn't realize.
Yeah. So the R for N is L, and the R for friction is L. The R for gravity is the one that has L over 2.
Thank you.
Okay, sure. Okay, so good. Any other questions? All right, so we've seen now a couple of these examples. I want to write down just sort of a set of steps. Here are the steps to solve these problems. And we can kind of refer back to this one to see what we did. So, steps for, net torque equals 0 problems. So step 1 is to draw an accurate picture. So what do I mean by an accurate picture? I mean the forces, we have to have all the forces and be located exactly where they are touching the object. So draw all forces with accurate locations. This is kind of fun when I'm writing on this thing when it's lagging, because it's like I get to write it and then I get to watch and see if the letters came out in the right place. Okay, so with accurate locations. So that's key. We've got to get the forces drawn in with accurate locations. Then we're going to draw in our vectors. Actually, sorry, we're not going to draw them in yet. We're not going to draw them in yet. We did. I should do it the way we actually, not the way it sounds like you should do it until you think about it. So what do you do after you draw the accurate picture? So then we have to choose a pivot point. And how do we choose it? We choose a pivot point to cancel out the quote worst torque. So what do I mean by the worst torque? I mean the one that we know the least about. So if there's a force in there where you know there's a force but you don't know its angle, that would be what I would call the worst torque. Okay. Sometimes there may not be a worst torque, so then you just pick a torque to cancel. Next, we're going to draw in our vectors from pivot point to each force. Okay. Now that step, the step 3, we might put it later too, but we might as well do it at this step. Next, we're going to write out net torque equals 0, with 1 torque per force. So each force gets a torque. We're going to fill in signs plus 4 counterclockwise minus 4 clockwise, 0 if R equals 0. So that allows us to cross out one of the torques. Then we solve for unknown. We use a table if it is complicated. So that is, if we've got probably more than 2 torques, you should probably make a table. You don't have to, but I find I make less mistakes if I do that. Let's see, complicated. Okay, so use a table if it is complicated. Now, if that turns out to be insufficient, then we may need net force equals 0 also. So if you try to solve for your unknown and you have too many unknowns, then that will mean you need to go to net force equals 0, and then that will allow you to combine equations and eliminate unknowns. If we do a good job choosing the pivot at the worst torque, we generally won't need to do that. But maybe if we pick a different pivot point, then we will have to do that. If we go back and look at the last problem, we actually needed that at a certain stage. When we were trying to fill in our table, we found out, oh, we don't know the normal force, let's find the normal force. So that's kind of where that step happens. When you're filling in the table and you realize you don't know enough, then you may have to go to net force equals 0 to fill in one of those blanks. Okay, so these steps, if you kind of keep those, maybe print it and keep it handy while you're solving problems and just try to follow these steps, you will see that this is a routine. It's a pattern. You don't have to be especially good at physics to follow this pattern. You just have to be able to, you have to be able to draw the picture accurately. That's key. So make sure you're really careful when you draw that picture. And then, like I said, if you choose the pivot point cleverly, you'll give yourself less work to do. So we'll see that as we practice today. Okay, any questions about the list of steps? All right, let's try some practice from the book. So I'm looking at the 3,000 Problems book, and we're going to do problem 10.22. It gives us a figure. It says that in the figure there is a beam with a certain weight and a weight hanging. Let me reproduce this picture. So we have kind of a hinge on the wall, and then there is a beam, a rod of some sort. And from the end of that, there's hanging a weight. And then there's little kind of a hook there that's attached to a rope. And it tells us that this distance between the end and where the rope is attached is 0.2 times the length, so 20% of the length. And then that means, of course, that this distance would be 0.8 L. Give us an angle of 60 degrees. And we are asked to find the tension in the rope and the x and y components of the force that the hinge exerts on the wall. So let's draw the forces in and then see how that relates to what they're asking us to do. So first of all, force of gravity, right there in the middle. Then we're going to have a force that is downward. That's on the end of the rod. So I'm drawing forces on the rod. The force that's downward, I'm just going to call that W. This one, I'll call it Fg. They tell me that Fg is 60 newtons, but the W is 200 newtons. So I'll just put that in the picture so that I don't have to go back and look at the English later. What else do we have? We're going to have some tension in the cable. And then there is a force from the hinge down here. Now, I do not know which way this force is pointing. I'm just going to point it in kind of a generic direction up and to the right. But let's talk about why I think it might be up and to the right. Now, it doesn't matter if it's not up and to the right. That's not going to affect me in any way. I'll just get negative components for that force's components, and that will tell me what it really looks like. But I just draw it in a generic direction in the first quadrant. Now, why do I think it's up? Because I've got the two forces of gravity. The force of gravity and the weight are both down, and there has to be something supporting this rod. So there must be something with an upward force, and the tension is perfectly horizontal, so it has to be coming from the hinge. Second of all, the tension is pulling to the left, so there must be something pushing to the right to balance it, and that also has to come from the hinge. So just kind of from a perspective of vectors, if I'm doing something is down and something is down and something is to the right, but the vectors to add up to 0, then the missing vector must point up and to the right, okay, in order to get me back where I started. So that's kind of my thinking. Now, we have basically 3 points of contact on the rod. The left edge where the hinge is, the right edge where the weight is hanging, sort of 80% up where the tension is, and that's 3 forces, and then gravity makes the 4th force. So I know I got all of them, okay? So what did I do so far? I drew in an accurate picture. I made sure each of the forces is located at the proper place where I can tell where it is, okay? So that's step 1. Now we want to choose a pivot point to cancel the worst torque. So which torque is the worst? Well, force of gravity and W are pretty good because I already know how big those forces are. I know exactly where they're located. I know the angles that they're located. I know everything about them. So I don't want to cancel one of those. The tension, I don't know the tension, so that one might be a good one to cancel. But I do know its direction. The force from the hinge, however, I don't even know the direction for sure. So the best choice would be to put my pivot point down there. And that's also, I honestly, from an intuitive standpoint, that makes sense as a pivot point because it looks like if the rope breaks, that's where it's going to swing. It's going to swing around that point. So conceptually, it's easier too. So we choose the pivot point, okay? We've chosen it to cancel the worst torque. Now we're going to draw in our R vectors. So let's see. For RG, we get something going from the pivot up to the center of this rod. For RT, I'm going to do these just in different colors to help us see them a little better. So for RT, it's going, I'm using blue for that. It's going from the point up to about 80% of the way up where the tension is connected. And for the next one, RW, using purple, That goes from the pivot point all the way up to the far edge. So colors are helpful because you get so many vectors going around, but once you've been doing this for a while, you can actually just visualize those R's, and you don't always have to draw them in once you have a good sense of what they should look like. Okay, so we did step 3, which is to draw in the R vectors. Now we're going to write out our net torque equation. That's going to be, there's a torque from the hinge, a torque from the tension, a torque from gravity, and a torque from the weight. That's step 4. Step 5 is to fill in the signs. And of course, the sign of torque hinge is 0. There's no sign because it's canceled out. For the tension, I can see the tension is trying to bring this thing counterclockwise. So it's going to get a plus sign, while the other two are trying to make it go clockwise, and they get minus signs. Again, if you have trouble visualizing this, hold your pencil at the bottom tip, hold it at an angle, and then, you know, push in the direction of the forces and see which way it rotates. That will help you figure out if it's going to go clockwise or counterclockwise. Okay, so that was step 5. We filled in the signs. Now we're going to solve for the unknown. So in this case, we're looking for the tension. So we get torque tension on its own. Torque tension equals torque G plus torque W. And we're going to fill in our formulas. R, T, T, sine of theta T equals RG, FG, sine of theta G plus RW, W, sine of theta W. And the algebra, the nice thing is the algebra is basically the same algebra every single problem. So, you know, if you are someone who likes, you know, something like 10 repetitions to really get something down, you truly get, you know, a lot of repetitions of the exact same algebra as you work these problems. So they start to look very, very similar as we do more and more. Okay, so now I'm going to fill in a table just to kind of make sure that I know everything that I'm supposed to know. Okay, so we need RG, and we need FG, and theta G, RW, W, theta W, RT, and theta T. So there's 8 variables we need to know. And then I go through my picture one by one. RG from the pivot to where force of gravity is, that's just going to be L over 2. That's the gravity goes right in the center. And again, that's unless the problem tells us otherwise. Normally, it will say something like a uniform rod. So this one says in figure 10.16, the beam is uniform and weighs 60 newtons. So it tells us it's uniform, and that's a key word for put the force of gravity in the middle. It says its weight is 60 newtons, so force of gravity is 60 newtons. And the theta G, I have to use my picture. They gave us an angle of 60 degrees between the wall and the rod, and that would mean this is also 60 degrees between the force of gravity and the rod. Then we have an R for the weight. That looks like the entire length, L. And the weight is given as 200 newtons. And the theta weight, that's also going to be 60 degrees. Then finally we have the R tension, which is 0.8 times the length. And the theta tension, since this lower angle is degrees, this angle on the top must be 30 degrees because we're getting a right triangle between the wall, the rope, and the rod. So So I do have numbers for everything except I don't have a number for the length. However, all of the R's are expressed in terms of L, and it's going to happen a lot that the L's just cancel. So let's see what we get. We have 60, L over 2 times 60 times sine of 60 plus L times 200 times sine of 60 all over 0.8 L sine of 30. And again, the L's cancel, leaving a 1/2 on the first term, a 1/2 times 60 sine of 60, and then a 200 sine of 60. So that's going to be 30 sine of 60 plus 200 sine of 60 over 0.8 sine of 30. I get 498 newtons. Okay, so we were able to solve tension using only, we did not have to use net force in the x direction or net force in the y direction. Okay, any questions? Okay, so let me finish this. We need to find the x and y components of the force from the hinge. So here we want to maybe reproduce our picture on a new page. And use net force in the x direction equals 0, and net force in the y direction equals 0. So in the x direction, we're going to have F hinge x minus t. And in the y direction, we're going to have F hinge y minus Fg minus W equals 0. So the F hinge x is just equal to tension, which is 498 newtons. And the F hinge y is just equal to Fg plus W, which is 260 newtons. So that's what it asked us, to find the components of this. But on a different day, we might be asked to find the magnitude and direction. So just to remind you, with our vectors, then what is the magnitude of F hinge? We use the Pythagorean theorem. And get 562 newtons. And the angle for the hinge would be the inverse tangent of y over x, 260 over 498. And that is 27.6 degrees. Okay, so I drew it in the correct quadrant. I have a positive x and y component, but if I had a negative y component or a negative x component, I would figure that out just and find a new angle, and that would tell me my picture was wrong, but that does not matter because I didn't use the way it looks in the picture for anything. Okay, any questions? Haley.
I was just wondering, so when you drew like the weight at the end, is that like hanging from a string too? Like how do we know there's not tension, there also?
Yeah, that's a good question. So what's really happening is, yes, it's hanging from a string. And there is tension. So what happens is we have W, and then there's tension. So I'm looking at forces on the box. So when I sum the forces in the y direction on the box, I get T minus W equals 0. So the tension is just equal to the weight. So what's really happening is there's a tension on the top. So that's really what there is. But I just already know the tension is going to be equal to the weight. So I just cut corners and just called it W. Does that make sense?
Yeah.
Yeah. If this thing is not in static equilibrium, like it's moving up, then the tension might be bigger than the weight, and then I would have to be much more careful. Okay, good. Other questions? No questions? Okay, so we're going to take a short break. When we come back, we will do some more problems. Okay, maybe 5 minutes.